Okay. Now, sometimes we're going to run a chi-squared test for independence. Guess what? 3 conditions. Imagine that. Just like every other significance test we've done all year. Same 3 conditions even. Random? Yeah. Did they tell us or not? 10% condition. Is the population at least 10 times the size of the sample? And then large count. All expected counts, at least 5. The same conditions for goodness of fit and the same conditions for the test for homogeneity. No different. Okay. Now, what does the chi-squared test statistic look like? Check it out. It's the same exact test statistic that we've used for the previous 2 problems. So we don't have to learn anything new here. It's going to be for a two-way table. So how do we find the degrees of freedom? We already know that. Row -1 times column -1. So there's nothing different in the mechanics of conducting a chi-squared test for independence versus a chi-squared test for homogeneity. Same exact process. The only difference is how we write the null and alternative, but the process exactly the same. So let's take a look at a problem that would be for independence. Okay. Remember this problem we did with the snowmobile and the environmental club members? Okay. We already did this problem with this two-way table in chapter 1. We did quite a few examples with this. They ask us first, do you belong to an environmental club like the Sierra Club? Yes or no? Right? That's the first variable. What is your experience with the snowmobile? Do you own one? Have you rented one, or have you never used one? Okay. Do these data provide convincing evidence of an association? Wait a minute, association, we said this test was going to be for independence. Well, if you recall back to the probability unit, that an association means that they are not independent or that they are dependent. Okay. So an association is another way to say that they are dependent upon each other. Independent means there is no association. Association means that they are not independent or they are dependent. So the question wants us to answer that. Is there an association between the environmental club status and the type of snowmobile use? Well, let's find out. I'm going to number these again like I did in the previous problem because I think it might help us if we think about all of these significance tests as a 4-step process. Okay, first, what are we going to do? What's our plan? What's the variable of interest and what's going on? Okay. All right. So remember, the null is always there is no difference. So for a test for independence, that means that there is no association. No association between what? There's no association between the 2 row and column variables. So there's no association between environmental club status and snowmobile experience. And I write show. Let's at least fix that spelling. I know I've had lots of spelling errors, but that one's pretty bad. Okay. Environmental club status and snowmobile experience. Guess what the alternative is then? There is an association. I think these known alternatives for chi-squared are pretty easy for us to write once we determine, is it a homogeneity test, is it a goodness of fit test, or is it a test for independence? An independence test is association. Are they related? If I know that you're a member of the environmental club, can I predict your snowmobile experience? That's what we're really trying to answer. Now here I should technically write out between environmental club status and snowmobile experience, but just to save time and to save some room on this page, you guys can fill that in on your own. Step 2, check conditions. Okay, random, I don't know. Yep, they tell us. it states at the very top that it was a random sample of winter visitors to Yellowstone National Park. All right. Next, 10% condition. We'd have to assume what? That there are more than 15,260 who's where? More than 15,260 winter visitors to Yellowstone. We're safe there. They have more than that many visitors in a day. So yes, there are definitely more than 15,260 winter visitors to Yellowstone. So the 10% condition has been satisfied. Okay. What about the large count condition? Well, like we did in the last problem, I don't necessarily want to go find each and every one of these expected counts. I could do it. So let's look at how we would do one of them. How would I find the expected count for never used a snowmobile and not a member? Remember, it's row total times column total divided by table total. So the expected for the never and no member would be row total 657 times column total 1221 divided by table total 1526. However, I'm not going to do that for all four of these. It just takes too much time. So instead, let's let the calculator do all the work for us. Let's let the calculator do the heavy lifting, right? It's the muscle, we're the brains. So I'm going to go in here to remember matrix, second x inverse, and I want to edit matrix A. What kind of matrix do I have? Oh, this is a 2 by 2. It's like, all right, cool. Put the numbers in. 445 goes in the first cell, 212 into the second cell, 497 into the third cell, and 77. Cool. I got my matrix populated. Now I'm ready to run my test. Stat, test. Now, this is just a chi-squared test. The goodness of fit is only for when we have one variable and not two. So I want to run a chi-squared test. It's going to ask me, where'd you put your observed? Yeah, I put it in matrix A. Expected? No, I didn't do my expected. You're going to do it for me. Calculate. Cool. It did the work for me. Now let's see what the expected counts were. So we need to go back into our matrix and we need to edit matrix B. We're not really going to edit it, but that's what's going to allow us to see what's in here. Yeah, all of them are way bigger than 5. So we're fine there. Okay. Probably for time's sake, I should have wrote down the important information on the test before I went to check my large count, but I was just trying to do things in order here with you guys. So all expected, I don't know why I switched to red, are greater than or equal to 5. Absolutely they are. Okay. Now I got to run that test again to see the important information. So stat, test, chi-squared test. Oops, one too many. Okay. Yes, A and B. I already got the data entered. So it's going to tell me for step 3, chi-squared is 60.61. Degrees of freedom is 1 because this is a 2 by 2 table. So it's 2 minus 1 times 2 minus 1 gives me 1 degree of freedom. The p-value, they tell me, in this case, is really, really small. 6.9 times 10 to the negative 15th power. So that means 0.14 zeros and then a 6.9. Tiny, tiny, tiny little p-value. What does a little p-value tell us? Oh, the data is statistically significant. They affect the null and conclude that there is an association between environmental club status and snowmobile experience. This shouldn't be all that surprising, right? People who are a member of the environmental club are probably less likely to drive snowmobiles. They want to go out there and take care of nature, not go out and have fun and rip up the snow. So small p-value, reject the null in favor of the alternative. All right, let's look at one more example here so that we can see if we can determine the difference between these different types of tests. And also we need to be able to look at the computer printout. Okay. Here's a problem about, are men and women equally likely to suffer lingering fear from scary movies as children? Okay. So are boys and girls scared the same from watching a horror show? Researchers asked a random sample, good, we know it's going to be random, of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. More than 1/4 of the students said that some of the fright symptoms are still present when they are awake. The following table breaks down these results for us. What I want to focus on for this example is this computer printout here. Remember, we spent a lot of time looking at computer printouts when we did linear regression. Chi-squared is also one of these things in statistics that's very common for a computer to do all the work for us and just give us the important information. So let's kind of dissect this table real quick. You notice that male, yes, there's a 7 right here. Well, where'd that come from? Oh, that's the observed. Underneath it, there's 11.69. Huh, where'd that come from? Oh, that is the expected number of males who said yes. So these go together. And then there's this 1.883. Well, that's the chi-squared component for that. This 1.883 number here came from 7 minus 11.69 squared divided by 11.69. So that's how the chi-squared test statistic is calculated, by that observed minus expected squared over expected. Well, this computer did all the work for us. Sweet. Okay, they gave us the two-way table, they gave us the observed, they gave us the expecteds, they gave us the chi-squared values, they told us the degree of freedom down here, they gave us chi-squared down here, and well, check that out. They even did the p-value for us. How nice of them. This computer printout did all the work. So what does that tell you? That's not the important part. We know you guys can push buttons and go through the mechanics of calculating. The important part of what we're doing is, what the heck does it mean? Okay? What is this telling us? So let's take a minute to look at a couple of these questions. Should a chi-squared test for independence or a chi-squared test for homogeneity be used in this setting? So are we testing to see if there's a whole bunch of different populations that all act the same, or are we testing to see if there is a relationship within the same population? So this is a test for independence. The data was produced using a single random sample of college students who were then classified according to 2 variables. So since all of this data came from the same population, we're looking at a test for independence. Remember the test for homogeneity example we did? We were looking at, do Australians, UK, and US people react the same? So we're seeing, were they homogeneous? Were all those different populations the same? Where a test for independence, all the data comes from the same population, and we're checking to see if there's a relationship or an association between the two. So this would definitely be a test for independence. State an appropriate pair of hypotheses. Well, since it's an independent test for independence, we know that the null is going to be there is, no association between what? Between gender and fright symptoms. What do you think the alternative is going to be? Yeah, you guessed it. There is an association between gender and fright symptoms. So part A is a test for independence. Why? Because the data came from the same population. Part B, state the null and alternative. We did that. Here's our null and alternative. Part C says, which cell contributes the most to the chi-squared test statistic? So you can see, let me get back to my red pen. You can see here are the contributions to the chi-squared. Okay. These four values were the ones added up to make this 4.028. So which one contributed the most? Oh, the male, yes. So that would be male, yes, for the answer to part C. It was the most different. It's contributed the most to that chi-squared test statistic. Interpret the p-value, and what conclusion would you draw? So the p-value is 0.045. So what does that mean in context of this problem? So assuming the null is true, or in this case, assuming there is no association, the probability of finding a sample such as the one we found would only happen .045, the proportion of the time, or if you'd like percents, would only happen 4.5% of the time due to chance alone, due to sampling variability. Is that statistically significant? So is this 0.045 less than this stated alpha level of 0.01? No. Therefore, the data is not statistically significant. Okay. So the data is not statistically significant. We fail to reject the null. We do not have enough evidence to say that there's a difference in gender and fright symptoms. Okay. We do not have enough evidence to say there is an association. We do not have enough evidence to claim an association between, I'm running out of room here, I'm gonna have to squeeze this in, between gender and fright. All right, so that's chi-squared. Remember the three different tests: goodness of fit, homogeneity, independence. Process is the same. Chi-squared test statistics calculate the same way. Observed minus expected squared divided by expected. Find the sum of all those. Okay. The null and alternative are different between the three. Okay. Step two, the conditions are identical. Random, they tell us or they don't. Large counts, all expected counts are greater than 5. 10% condition, population must be at least 10 times the size of the sample. How do we calculate the chi-squared test statistic? The same for every problem. Okay. How do we find the p-value? Same for every problem. The degrees of freedom varies. Remember, for goodness of fit test, it's k minus 1, the number of categories minus 1. However, for homogeneity and independence, it's rho minus 1 times column minus 1 to get our degrees of freedom. And then our interpretation is based off of our null and alternative. So it's different for each one depending on what null and alternative that we wrote.